Have you ever explored whether we're truly alone in the universe? Or, then again, have you considered that there might be something beyond what we see? Envision what is happening and think about how conceivable it is that the James Webb Space Telescope will finally show that we live inside a dark hole. Join us as we uncover more about this world and spread the word that will make you question everything you thought you knew about the universe. So, what exactly are dark holes? They're like something out of a spine chiller. Sure, you might have seen them in sci-fi films, but what's substantially more disturbing is that they're not just a made-up idea. According to well-informed experts, dark holes in space are truly enormous amounts of matter pressed into an incomprehensibly infinitesimal area. Imagine a star a few times more massive than the Sun, all packed into a space the size of New York City. The gravitational pull is so extreme that nothing, not even light, can escape from it. Scientists have been fascinated by dark holes for a long time. At first, they concentrated on objects in space so huge and thick that they could trap light. The most striking ideas about dark holes were proposed by Einstein's theory of general relativity. Basically, when a gigantic star dies, it leaves behind a thick core. If this core's mass is a few times that of the Sun, gravity overwhelms everything else, leading to the formation of a dark hole. It isn't simple to detect dark holes, as they emit no light. However, analysts have found ways to interpret their presence by observing their effects on neighboring matter. For instance, if a dark hole passes through a cloud of interstellar matter, it will pull matter toward it in a process called accretion. Moreover, when an ordinary star gets too close to a dark hole, it can be destroyed, producing X-rays as it does so. Dark holes also have a huge influence on their surroundings. They can consume nearby stars, reduce extreme light emissions, and even influence the formation of new stars in certain regions while stifling it in others. So, how do dark holes form? Picture this. Stars once brilliant and shining meet their fiery end in a massive explosion called a supernova. From the remnants of these fallen giants, dark holes emerge. Most dark holes form from massive stars that have reached the end of their life cycle in a supernova. However, smaller stars, when they die, turn into something many refer to as neutron stars, which are incredibly dense but not dense enough to trap light. However, if a star is a few times the mass of our Sun, it collapses under its own gravitational force, forming a dark hole. As these giant stars collapse, something astonishing happens near their surfaces. Time itself begins to play tricks. From the perspective of someone far away, time appears to slow down near the event horizon, the last defining point for anything falling into a dark hole. The clock ticks at a different speed compared to ours on Earth. Occasionally, when two smaller dark holes collide, they merge to form a much larger and even more frightening dark hole. If a dark hole interacts with a neutron star, it creates an unbelievable nightmare that defies understanding. Scientists have been grappling with the size of these cosmic anomalies for quite a while. Dark holes come in two sizes, big and small. However, there's a bit of a misunderstanding about them. Small is relative when it comes to dark holes. Very large dark holes, remnants of gigantic stars, can be as much as 10 million times the mass of the Sun. There could be upwards of 10 million to a billion of them in the Milky Way alone. That is a colossal number of dark holes that could swallow anything in their path. But wait, there's more. Extremely large dark holes exist at the extreme end of the spectrum. They are millions, if not billions, of times larger than the Sun. These inhabit the centers of massive galaxies, including our own Milky Way. They appear like a massive dead space, pulling everything toward them. The renowned physicist Stephen Hawking discussed dark holes throughout his life. His theories were well established, but some of his ideas proved difficult to confirm due to a lack of advanced technology. However, there is now hope on the horizon. Not too far off, a single revolutionary instrument is changing everything: the James Webb Space Telescope, JWST. Let me tell you, the JWST is no ordinary telescope. It's an engineering marvel, a demonstration of human ingenuity. Sure, we've launched other space telescopes before, and they've done their jobs competently, but this extraordinary machine is on a level that is truly remarkable. The JWST makes the Hubble Space Telescope, which has served us for so long, look like a basic tool. The retail cost of this enormous wonder is a staggering $1 billion. Yes, you heard that right, an eye-watering number of zeros. It took the combined efforts of NASA, the European Space Agency, and the Canadian Space Agency to bring this marvel to life, along with enormous contributions from more than 300 universities. However, we shouldn't forget the risks associated with such a grand undertaking. I understand that this isn't a venture for the faint of heart. The JWST is venturing into uncharted territory, expanding the boundaries of what we know and taking us to places we've only dreamed of. Following a successful launch, NASA recently announced that the telescope has enough fuel to last several times its original mission life. Since its launch, the JWST has already made several groundbreaking accomplishments, traveling more than 1 million miles to reach its orbit around the Sun, where it will live indefinitely. During its journey, the telescope successfully deployed its massive 5-layer sun shield and enormous primary mirror, both of which had to be folded to fit onto the launch vehicle. Now, after alignment and adjustments, the telescope is nearly ready for full operation. One of the most exciting parts of the James Webb Space Telescope's mission was when NASA reported that it had captured its first significant images of starlight. The first image taken by the telescope was of a star called HD 8446, revealing a series of 18 dispersed brilliant spots from the star's light gathered by the 18 mirror segments arranged on the primary mirror. NASA later released another stunning image of HD 8446, where 18 unfocused copies of the star were arranged in a deliberate hexagonal pattern. Once the observatory adjusts the individual segments of the primary mirror, it will begin the process of stacking images on top of one another to create one clear view. Thanks to its cutting-edge technology, the JWST will help scientists study the early stages of the universe after the Big Bang. It will focus on what happened after the first stars formed, a period known as the epoch of reionization. This refers to when neutral hydrogen was reionized, given an electric charge once again by radiation from these first stars. This involves looking back billions of years, which is only possible with a powerful telescope like the JWST. The telescope will also help scientists discover exoplanets, which are incredibly challenging to detect because of how they interact with their host stars. Observations can now closely study these planets, allowing scientists to analyze their atmospheres and explore the conditions necessary for life. The JWST's capabilities will help researchers better predict whether specific planets may be habitable. After studying planet formation, scientists focus on these worlds to understand how matter is organized on a massive scale. This, in turn, helps us understand how the universe has evolved, forming the worlds we see today billions of years later. One of the JWST's objectives is to look back at the earliest galaxies to better understand how they formed. Scientists are also trying to determine how we got the variety of galaxies we see today, as well as the ongoing processes that lead to the formation and merging of galaxies. To unravel this, the James Webb Space Telescope is certainly at the forefront of this exciting scientific journey. With its ability to observe distant galaxies, stars, and even exoplanets in unprecedented detail, it has already provided a glimpse into the depths of the universe and has shown that we may not be as alone as we once thought. One of the most mind-boggling revelations from the JWST is its ability to detect molecules such as polycyclic aromatic hydrocarbons, PAHs, around supermassive black holes in galaxies billions of light-years away. These organic molecules, which could potentially be the building blocks of life, are found in dense gas clouds near black holes, hinting at the possibility that life could exist in places that we previously thought were inhospitable. The fact that these PAHs can survive near black holes, where the gravitational forces are extreme, further fuels the idea that life might not be restricted to just one corner of the universe. Moreover, the JWST has also uncovered the most ancient black holes, dating back to the dawn of the universe, just 570 million years after the Big Bang. These early black holes are not only massive, but their discovery challenges current theories about the formation and growth of black holes in the early universe. Astronomers now speculate that there may be even older black holes yet to be discovered, hidden deep within the cosmos. In addition to investigating black holes, the JWST is providing valuable data about the formation of stars and galaxies, shedding light on the processes that led to the cosmic structures we observe today. It is also enhancing our understanding of exoplanets and their potential to host life. By studying the atmospheres of exoplanets, scientists can now identify the presence of gases such as water vapor, methane, and carbon dioxide, key ingredients for life as we know it. The telescope's infrared capabilities allow it to detect faint signals from these planets, even those that are light years away, helping to answer the age-old question: are we alone? These groundbreaking discoveries also bring us closer to understanding dark matter, a mysterious substance that constitutes a significant portion of the universe's mass but remains elusive to current detection methods. Some theories suggest that primordial black holes, formed shortly after the Big Bang, could be responsible for dark matter. If this theory holds true, it would open up a new avenue of research into the very fabric of the universe. As the JWST continues its mission, it will undoubtedly revolutionize our understanding of the cosmos. The possibilities it opens are vast, from uncovering the origins of galaxies and stars to exploring the potential for life beyond Earth. Each new revelation will bring us one step closer to solving some of the universe's most profound mysteries, ultimately helping us understand not only where we come from but also whether we are truly alone in this vast, mysterious universe. As we continue to peer deeper into the cosmos, the James Webb Space Telescope, JWST, is poised to challenge our understanding of the universe in ways that were previously unimaginable. The telescope's capabilities stretch beyond simple observation. It allows us to investigate the birth of stars, the dynamics of galaxies, and the complex processes that give rise to life-supporting conditions. As technology advances, we are continuously breaking down the walls of our knowledge, inching closer to answers to some of the universe's most profound questions. One of the most exciting aspects of the JWST is its ability to capture images of distant galaxies as they appeared billions of years ago. Since light travels at a finite speed, the farther we look into the universe, the further back in time we are able to see. The JWST is equipped with highly sensitive infrared technology, allowing it to peer through the dust clouds that often obscure distant cosmic objects. This means it can detect faint signals from objects in the early universe that were previously invisible to older telescopes. This breakthrough is providing astronomers with a rare glimpse into how galaxies formed, evolved, and merged, giving insight into the forces that shaped the universe we live in today. Moreover, the JWST is redefining how we study the composition of distant worlds. With its enhanced ability to detect atmospheric elements, it can analyze the chemical makeup of exoplanet atmospheres in unprecedented detail. For the first time, we can begin to detect the faintest traces of gases like oxygen, methane, and carbon dioxide. These are the same gases associated with life on Earth, prompting researchers to wonder whether similar processes could occur on exoplanets in other solar systems. The JWST's advanced spectrographs will help scientists determine whether any of these planets are capable of supporting life, potentially identifying distant worlds that could harbor living organisms. The study of exoplanets has long been a subject of fascination. Before the advent of telescopes like the JWST, we were limited to detecting the presence of exoplanets only through indirect means, such as their effect on their host star. However, the JWST's ability to study these planets directly is revolutionizing our understanding of exoplanetary atmospheres. With its sharp infrared vision, the telescope is able to detect temperature variations, weather patterns, and even the presence of clouds on exoplanets. This data will be crucial for scientists as they refine their models of planetary habitability and begin to assess the potential for life beyond Earth. Another major area of research is the JWST's exploration of the formation of stars. When a star is born, it emerges from a dense cloud of gas and dust. The process is complex and can take millions of years to unfold. The JWST's unparalleled sensitivity allows it to observe this process in real time, tracking the growth and evolution of stars from their earliest stages. By studying these stellar nurseries, astronomers can learn more about the conditions that lead to star formation and the ways in which these stars influence their surrounding environments. The JWST is also providing valuable insights into the elusive nature of dark matter. While we cannot yet directly observe dark matter, its gravitational effects are evident throughout the universe. Scientists believe that dark matter makes up roughly 85% of the universe's total mass, yet it remains invisible to current instruments. The JWST is designed to study galaxies and galaxy clusters in such detail that it may uncover clues about the distribution and properties of dark matter. Through the observation of gravitational lensing, where light from distant objects is bent by the gravitational pull of dark matter, the JWST could offer crucial insights into the nature of this mysterious substance. The telescope's mission isn't limited to just exploring our corner of the universe. One of the JWST's most ambitious goals is to study the conditions present in the early universe, just moments after the Big Bang. By looking at the formation of the first galaxies and the early stages of star creation, the telescope is helping scientists understand how the universe evolved from a hot, dense state into the complex structure we see today. These early galaxies are some of the most distant objects we can observe, providing a snapshot of the universe's infancy. By studying these galaxies, researchers hope to uncover more about the processes that led to the formation of stars, galaxies, and the elements that make up our world. In addition to galaxies, the JWST is also shedding light on the formation of supermassive black holes. These monstrous objects, millions or even billions of times the mass of our sun, lie at the centers of most galaxies, including our own. While their formation remains an area of intense research, the JWST's advanced capabilities allow astronomers to study their growth and evolution in greater detail. By observing the interaction between supermassive black holes and their surrounding galaxies, the telescope can help us understand the role these objects play in shaping the structure and behavior of the universe. Another fascinating aspect of the JWST's mission is its study of the origins of life. The discovery of organic molecules in space has long been a subject of intrigue, and the JWST is providing the tools to study these molecules in greater depth. Organic compounds, including those that are the building blocks of life, have been found in the interstellar medium and around black holes, suggesting that the ingredients for life may be more widespread than previously thought. This opens up the possibility that life could exist in environments we once thought were too hostile to support it. The JWST's ability to detect complex organic molecules and analyze their chemical composition will be instrumental in unraveling the mystery of life's origins. As the JWST continues to gather data, it is rapidly transforming our understanding of the universe. From studying the formation of galaxies to investigating the potential for life on exoplanets, the telescope is unveiling the mysteries of the cosmos in unprecedented detail. The data it provides will not only answer long-standing questions, but also spark new lines of inquiry, leading to even more discoveries about the nature of our universe. The groundbreaking research conducted by the JWST will undoubtedly shape the future of astronomy and inspire generations of scientists to continue exploring the cosmos, bringing us closer to answering the ultimate question: are we truly alone in the vast, infinite universe?